It has the capability to do computations that would take hundreds, thousands, maybe even millions of years on even the biggest supercomputers that are out there today.
Microsoft's quantum AI chip was once hailed as a monumental achievement in modern technology, a symbol of human innovation and a window into the evolution of artificial intelligence. But something extraordinary and completely unexpected has now taken place. Scientists involved in its development have been left in disbelief, as reports suggest the chip has somehow tapped into alternate dimensions. The question now looms large. What could have driven this device to surpass the limits of our known reality? Are we witnessing a revolutionary new era unfolding before our eyes? Or have we opened a door to something far more hazardous? The implications of this event may reshape everything we thought we understood about existence and the universe itself. To comprehend the gravity of this development, we must first examine the fundamental differences between classical and quantum computing. Traditional computers operate using bits, the smallest units of data, which exist in one of two possible states, either a 0 or a 1. These bits serve as the digital language of modern computing, forming the foundation of everything we use, from text documents and photographs to games and video streams. While efficient and practical for many standard tasks, this binary system encounters severe limitations when addressing problems that require immense computational power or intricate modeling. Quantum computing introduces a radically different concept at its core. Instead of relying on binary bits, it utilizes quantum bits or qubits. Unlike their classical counterparts, qubits can exist in a superposition, allowing them to represent both 0 and 1 simultaneously. Picture flipping a coin that never settles on heads or tails but hovers between both outcomes until you observe it. This bizarre but powerful phenomenon allows quantum machines to process enormous quantities of data all at once, as opposed to step-by-step like classical systems. Consider the example of navigating a complex maze. A conventional computer would methodically try each path one by one, potentially requiring extensive time to find a solution. A quantum computer, thanks to the properties of superposition, can evaluate numerous paths concurrently, drastically reducing the time needed to solve the puzzle. This quantum advantage isn't simply a matter of increasing processing speed. It enables entirely new kinds of problem-solving approaches that were previously thought impossible. This capability is particularly transformative in fields such as advanced chemistry and materials science, where the behavior of molecules and atomic particles is dictated by the principles of quantum mechanics. Traditional computers can only simulate these processes using rough approximations, leading to limited accuracy. With quantum computers, however, scientists can model reactions at the level of electrons and protons, which could pave the way for groundbreaking discoveries, such as developing revolutionary pharmaceuticals or engineering self-healing materials. This is no longer a distant possibility. It's an emerging reality, poised to revolutionize how we address some of the most challenging scientific questions of our time. Microsoft's journey toward developing this powerful quantum chip, known as Majorana, was neither swift nor simple. The origins of this ambitious undertaking trace back to 2004, when the company, in collaboration with various research institutions, embarked on a mission that many deemed impossible: to turn a purely theoretical particle into practical, functional technology. At the heart of this mission was the Majorana fermion, a unique particle first theorized in 1937, believed to exhibit behavior unlike anything seen in classical physics. Most notably, it is thought to be its own antiparticle, a trait that defies conventional understanding and makes it exceptionally difficult to work with. The early phases of this effort were riddled with difficulties. Researchers faced numerous setbacks and false starts as they attempted to convert abstract quantum theory into physical application. In one notable instance, a key paper published by Microsoft in 2018 had to be retracted after its foundational assumptions proved premature. However, such failures did not deter the team. On the contrary, each obstacle only strengthened their resolve to solve the enigma of the Majorana particle. The turning point came when Microsoft's physicists and engineers identified a previously unknown phase of matter, a topological state that didn't fit neatly into any known category like solid, liquid, or gas. This discovery enabled the creation of an entirely new material known as a topological conductor. Imagine this material as the successor to traditional semiconductors, It doesn't just carry electrical currents, but also provides an exceptionally stable and noise-resistant environment in which qubits can operate effectively. With this foundation in place, Microsoft developed topological qubits, an entirely new breed of quantum bit far more robust and less susceptible to the disruptions that plague most other quantum systems. Typically, qubits are incredibly delicate, easily destabilized by even minute environmental changes. They are like crystal ornaments that shatter under the slightest pressure. The Majorana chip, however, incorporates error resistance into the structure of its qubits, creating a system that is naturally more stable and dependable. This breakthrough eliminated the need for massive, room-sized cooling systems and elaborate shielding often required by other quantum computing setups. Instead, Microsoft's chip could host millions of these refined qubits on a surface small enough to fit into a human hand. The journey from obscure theoretical predictions to a practical, fully operational quantum chip demonstrates the immense dedication and vision behind this initiative. Every experiment, recalibration, and scientific breakthrough brought the team closer to shaping the future of computing itself. This chip is more than a technological curiosity. It is the product of a delicate dance between advanced physics and cutting-edge engineering. The design moves beyond the limitations of conventional qubits, tapping into the exotic properties of Majorana particles to achieve a new level of reliability. In typical quantum systems, qubits must be shielded from even the tiniest interference, which requires costly and complex setups. Microsoft's approach circumvents these issues by leveraging the topological phase to build qubits that are naturally safeguarded by the very material in which they are embedded. The chip's construction relies on a revolutionary new material engineered with atomic precision. Every component is crafted to microscopic detail, allowing for an efficient and highly organized layout. These qubits are astonishingly small, about 1/100th of a millimeter each, allowing Microsoft to compress incredible computational power into a chip that's no larger than a coin. This scale is especially significant when viewed in the historical context of computing's evolution, from room-sized machines to sleek mobile processors. The Majorana chip represents a similar leap forward in the quantum domain. Think of constructing a city out of huge, cumbersome blocks, each requiring its own crane to lift in place. Now imagine building that same city with tiny, perfectly shaped Lego pieces that fit effortlessly together. That's the kind of transformation Microsoft's chip brings to quantum computing, moving from clunky, error-prone systems to compact, scalable architectures that can be assembled with extraordinary precision and reliability. In a market where companies often compete by boasting higher qubit counts, Microsoft has chosen a more strategic path. Rather than focusing on raw numbers, they have prioritized the creation of qubits that are both compact and inherently resistant to failure. Their topological approach embeds error correction into the fundamental structure of the qubits, meaning that even a modest initial number can scale efficiently as the technology matures. The result is a platform that prioritizes meaningful functionality over flashy statistics. Microsoft's approach is reminiscent of the earliest days of personal computing. Simply having a machine wasn't enough. It had to be practical, efficient, and capable of performing useful tasks. Similarly, Microsoft has engineered its quantum system to deliver real-world results. Instead of pursuing higher specs for the sake of headlines, they are focused on solving hard, practical problems, like simulating molecular structures or designing advanced materials. Another crucial advantage of this approach lies in its simplicity and adaptability. While many quantum systems require massive, custom-built infrastructures to operate, Microsoft's chip is compact and efficient enough to fit within existing server environments. This means that quantum capabilities can be integrated into traditional computing networks without the need for sweeping architectural changes. It's a design philosophy that makes adoption faster and more affordable, an essential quality if quantum computing is to achieve mainstream relevance. Importantly, this technology is not just a promise on paper. As the number of usable qubits increases, from tens to hundreds and eventually thousands, the chip will become capable of handling real-world computational challenges. It could unlock new discoveries in science, medicine, and industry that are currently beyond the reach of classical computing. Microsoft's quantum design is more than just a technical marvel. It's a vision for the future of computation, one that brings the abstract possibilities of quantum theory into concrete, transformative reality. The practical uses of quantum computing have the potential to dramatically reshape numerous aspects of modern life, touching upon some of the most formidable scientific and technological puzzles we currently face. Among the most promising domains is the realm of chemical research and materials engineering. For decades, researchers have grappled with the immense complexity of molecular interactions, whether it's to formulate groundbreaking pharmaceuticals or invent substances with extraordinary properties like self-repair. Traditional computing systems have long been constrained by their reliance on rough approximations when trying to model such intricate behaviors. This limitation has often forced scientists to resort to extensive and costly hands-on laboratory trials just to verify theories. Quantum computing, however, introduces the possibility of executing molecular simulations with a level of detail and fidelity that mirrors the intricacies of natural systems themselves. Visualize the development of a next-generation catalyst capable of decomposing harmful microplastics in our oceans, or the invention of a futuristic building material that intuitively restores itself upon cracking, much like a car or structure that can autonomously mend its wear and tear without external intervention. This revolution isn't confined solely to material science. The medical field stands to gain tremendously from quantum advances. At present, the journey to discover effective medications can span many years, with researchers often navigating a tedious cycle of trial and error. But imagine the capability to virtually test a new compound's interaction with a specific human protein, with a degree of precision that mirrors an actual lab experiment. A quantum machine equipped to simulate the quantum behavior of electrons within molecules could offer unprecedented clarity into exactly when and how a medicine performs its function, or alternatively, reveal where it might induce harmful side effects. Such accuracy could not only streamline the drug development process but also pave the way for highly customized, precision-targeted treatments we've only theorized about. Energy technology is yet another frontier where quantum innovation could play a transformative role. Consider the urgent need for better batteries, ones that charge more rapidly, endure longer usage, and minimize environmental impact. With quantum computational tools, researchers would be empowered to explore and design new atomic-scale materials, potentially ushering in a new era of energy storage solutions that are not only more efficient but also more environmentally sustainable. Simulations that are currently too complex for classical machines, such as those used in predicting long-term climate behavior or analyzing the tectonic stresses beneath Earth's crust, could become significantly faster and more reliable through the use of quantum-enhanced computations. Moreover, the convergence of quantum computing and artificial intelligence presents an entirely new paradigm. Envision a future where experimental data generated by quantum simulations feeds directly into advanced AI systems, training them to make smarter predictions that would be nearly impossible to achieve with conventional data alone. It's akin to merging the power of an elite scientific research assistant with your digital tools, offering a dynamic feedback loop of insight and prediction. Companies like Microsoft are already imagining such a future, one in which AI models, supercharged by quantum-derived data, could help us forecast weather with greater accuracy, refine logistical operations like supply chain management, and even suggest radical innovations in science and technology that would otherwise remain out of reach due to computational constraints. In essence, quantum computing doesn't merely represent a technological enhancement of what we already have. It symbolizes an entirely new framework for solving problems that remain unsolvable by today's standards. With the advancement of chips like the Majorana and other pioneering developments, the horizon is expanding rapidly. A future where industries as varied as healthcare, energy, transit systems, and manufacturing are equipped to tackle formerly insurmountable issues may not be far off. But, as with any leap in technology, there are formidable obstacles to overcome. The field of quantum computing has long been synonymous with intricate difficulties, particularly around the fragile nature of qubits, the core units of quantum data. In many existing quantum architectures, even the slightest environmental disturbance, whether it be a tiny temperature fluctuation or minor background radiation, can destabilize a qubit, throwing off computations and introducing inaccuracies. It's much like trying to maintain a house of cards in the middle of a breeze. Any small nudge can collapse the structure. Scientists have spent years trying to resolve how to maintain qubit stability and fidelity under real-world conditions. What makes Microsoft's Majorana 1 chip especially noteworthy is that it tackles these issues at a fundamental level. Instead of relying purely on software-based methods to correct errors, this hardware is built with error resilience baked in. The chip leverages a unique topological state created by a novel conductive material, enabling each qubit to be inherently more resistant to external noise and disruption. Thanks to this built-in protection, the qubits are better preserved in their functional state, even in less than ideal surroundings. This advancement significantly reduces the need for massive, specially controlled environments to maintain system integrity. Unlike earlier quantum systems that required sprawling, custom-built facilities to support and stabilize a small number of qubits, the design of the Majorana 1 chip allows it to function under less restrictive physical conditions. The result is a far more practical and scalable approach to quantum architecture. Scaling has always been one of the major hurdles in the field. Having just a few dozen qubits is hardly sufficient when trying to model something as intricate as the electronic interactions within a complex molecule. Many of today's experimental systems require massive infrastructure, sometimes the size of entire warehouses, just to accommodate enough qubits for meaningful operations. Microsoft's breakthrough lies in its ability to embed as many as 1 million qubits onto a chip compact enough to hold in the palm of your hand. This achievement goes far beyond simply shrinking the hardware. It offers an elegant and effective answer to one of the biggest technical bottlenecks in quantum scaling. Because these ultra-small, highly stable qubits can be produced and deployed in large numbers, they pave the way for quantum processors to be integrated into existing computing environments, like conventional data centers already running powerful classical systems. Rather than replacing today's machines, these quantum processors are designed to operate alongside them, enhancing specific tasks and expanding computational boundaries. The challenges in quantum computing are substantial and often appear overwhelming. Yet if history is any guide, humanity has consistently overcome similar obstacles with patience and innovation. Just as we transitioned from clunky vacuum tubes to sleek silicon chips that now power billions of devices, so too are today's scientists refining their quantum technologies to the point where theoretical dreams become everyday tools. The progress represented by chips like Majorana 1 suggests we are leaving behind the phase of lofty speculation and entering an era of tangible, scalable quantum computing. Across an expanding mesh of interconnected data hubs, quantum computing is gradually embedding itself into the foundation of future technology. For decision-makers and forward-thinking investors, these advanced machines represent an extraordinary opportunity. Once real-world applications begin yielding concrete results, whether that's simulating complex chemical reactions, uncovering material innovations, or supercharging the precision of AI systems, the economic payoff could be massive. Organizations spearheading these developments may soon find themselves at the helm of a transformative industrial era, one in which current limitations in computing are replaced by instantaneous processing and novel frameworks for managing data and information. When quantum computing merges with artificial intelligence, the fusion forms an incredibly powerful alliance between two of the most dynamic scientific fields of our time. Individually, each is a marvel of modern engineering, but together they unlock capabilities that surpass anything previously imagined. Quantum devices are uniquely capable of performing complex calculations and processing astronomical amounts of data far beyond the reach of today's classical systems. When such expansive datasets are used to train AI, the resulting algorithms exhibit remarkable levels of precision and intelligence. Consider it this way. Picture the most intricate and powerful microscope ever built, one that can observe atomic-level interactions with extreme accuracy. This instrument gathers vast volumes of granular data about molecular behavior. Feeding that incredibly detailed dataset into a machine learning system gives the AI something extraordinarily rich to work with, allowing it to spot relationships and forecast outcomes with uncanny reliability. The implications of this are immense. It could enable a revolution in pharmaceutical development or lead to the creation of exotic materials engineered with specific characteristics. Microsoft has embraced this synergy by closely aligning its quantum initiatives with its strength in artificial intelligence. By channeling quantum-derived information into its AI models, the company is striving to build intelligent systems that perceive reality with a depth and fidelity unattainable by traditional methods. The outcome is a more refined and accurate artificial intelligence, one capable of transforming fields as diverse as medical diagnostics and advanced industrial engineering. In this role, quantum computing serves not just as a complement to AI, but as a powerful engine that magnifies its learning and reasoning capacity. This evolution is also bridging two previously separate scientific worlds. Researchers and engineers in quantum mechanics and artificial intelligence are beginning to collaborate in ways that were rare in the past. As quantum platforms grow more sophisticated, a future where classical and quantum computing operate in harmony seems inevitable. The benefits are already emerging. Better simulations, faster data processing, and AI applications that can handle levels of complexity and scale beyond anything previously achievable. These joint efforts are laying the groundwork for innovations that were, until recently, only dreams within the scientific imagination. Looking to what lies ahead, quantum computing promises a future filled with remarkable breakthroughs. Concepts that once seemed confined to abstract academic theory are now evolving into usable tools. Experts in the domain are focusing on a crucial benchmark: achieving systems equipped with between 50 to 100 fault-tolerant logical qubits. Reaching this point would mark a monumental advance in computational power. It would move quantum computers out of the experimental phase and into a domain where they could begin solving intricate problems that continue to challenge even our most advanced supercomputers. Envision a world where researchers hoping to design new energy storage materials could simulate the behavior of every electron and atom involved, all with unprecedented precision, before conducting a single laboratory experiment. This kind of power could drastically shorten the timeline for discovery and eliminate costly trial and error phases. And the significance goes far beyond the scientific realm. As quantum hardware becomes more accessible in research centers and industry data centers, it will begin reshaping the economy, inspiring new kinds of employment, and altering the way global enterprises operate. This future, where conventional computational limits are replaced by real-time, intelligent problem-solving, is not just a fantasy. It's on the horizon. The transformation is gradual but unmistakable. In the coming years, we can expect these systems to evolve steadily, starting with their adoption in elite scientific institutions such as national research labs. These early adopters will put quantum machines to work on complex, domain-specific challenges. Over time, as the technology becomes more scalable and available, businesses in various sectors will begin using quantum computing to refine their operations, enhance productivity, and create new products and services. What we're witnessing now is merely the initial momentum. Every minor advancement contributes to the broader architecture of a global quantum infrastructure. Eventually, these contributions will aggregate into a seamlessly integrated system, where quantum computing is no longer a novelty but a standard component of our digital ecosystem. The transition will seem less like a leap and more like the next natural phase in the long arc of human technological advancement. As we conclude this exploration of quantum computing, it's increasingly evident that we're standing on the edge of a profound transformation. Microsoft's Majorana 1 chip represents far more than an engineering success. It's a testament to human determination and the drive to explore the limits of possibility. Constructed with the help of the elusive Majorana particle and founded on an entirely new class of topological matter, this compact yet powerful chip embodies years of innovation, challenge, failure, persistence, and visionary thinking. This is more than an upgrade to existing systems. It's a fundamental shift in how we conceptualize and perform computation. Calculations that once required unfathomable time and energy may soon be completed in moments. The wonder of this moment lies not only in the science that made it possible but also in the vast potential for real-world change. This could mean the design of new materials capable of healing themselves, the discovery of medicines with astonishing accuracy, or the empowerment of AI systems with intelligence vastly superior to anything we know today. These are not minor steps. They are seismic changes in how humanity approaches problem-solving. While the journey ahead will undoubtedly include technical hurdles and setbacks, the progress achieved thus far is reason for hope. As systems incorporating error-corrected logical qubits become more widespread and research groups and startups begin experimenting with real applications, a surge of innovation will follow. This wave of discovery will impact not just the tech sector, but all aspects of modern life, from education and healthcare to manufacturing and sustainability. We're not simply turning a page in the book of technological progress. We are beginning an entirely new volume, one that will be written using the principles of quantum mechanics. From abstract concepts dreamed up by physicists in the 20th century, we've now built a physical device small enough to hold in one hand, yet powerful enough to revolutionize the world. And we are all a part of this unfolding narrative. This is a shared journey, one that is set to change how we think, how we work, and how we solve the most complex challenges facing humanity. The quantum era isn't just near. It's arriving fast, offering a world where innovation moves at the speed of thought and possibility, expands with every passing day. We stand not just at a crossroads, but at the entrance to an entirely new universe of discovery. The path forward is bright, filled with promise, and we've only just begun. If you've enjoyed this deep dive, be sure to explore more content by selecting the video now appearing on your screen. The quantum revolution is underway, and the most exciting chapters are still ahead.